Yeah, that's it. More of that, please. Let's start today's session by acknowledging the traditional custodians of the land upon which the festival is being held, the Yuggera people. I pay respect to Australia's First Nations, who we recognise as the first scientists and custodians of the lands and environments and all animate and inanimate objects within it. We acknowledge the importance of their legacy, passed from one generation to the next over 50,000 years, and the legacy that has on caring for Mother Earth and contemporary scientific conversations. I acknowledge the deep and timeless relationship between country and Aboriginal people and Torres Strait Islanders, and also pay respect to the elders of the community, both Indigenous and non-Indigenous, who are with us today. Welcome, ladies and gentlemen, to Pioneers in Science. Queensland Museum is proud to host the World Science Festival, and we thank our partners for their support. My name is Tegan Taylor, and I'm a science and health journalist at the ABC, but the people that you're really here to see today are some really incredible scientific brains. But before we meet one of them, I'll just set the scene. In 1998, a young astronomer who went to high school in Alaska was racing to study the expansion of the universe. He would go on to make a discovery that would completely change our understanding of the universe. The following year, a young Australian started her PhD to determine the impact of this discovery. Please allow me to introduce her to you now, ladies and gentlemen, Professor Tamara Davis.
Hi everyone. Hi Tegan.
So we're calling this Pioneers in Science, so let's get straight to the chase. What science have you pioneered?
Okay, so I do astrophysics and cosmology. So I study space as a whole. In terms of cosmology, astrophysics is the study of basically space, stars, how things work up there, and cosmology is going biggest picture. How did the universe begin? What are the laws of physics? How does the whole thing work? And where will the universe go? Like, how will it end? And
just
so,
little stuff like that.
Just the little stuff, you know. So I've been asking questions like, this discovery that you were just referring to was the discovery that the expansion of the universe, which we've known about since the 1920s, the expansion is speeding up. Now, we had always thought it should be slowing down because, you know, what goes up must come down. You throw things apart, gravity pulls them so that they come back together, or like they slow down, stop, and come back together. And that's basically what we thought was happening with the universe. The galaxies were all moving away from each other, but they should be slowing down. And the only question was, are they slowing it down enough that they'll stop and turn around and collapse, or do they have the escape velocity, so they're going fast enough that they'll keep slowing down, but the expansion would go on forever. So this discovery that was made in the 90s was that neither of those was actually true. The expansion is not slowing down at all, it's speeding up right now. We don't know what causes that acceleration, but we give it the name dark energy, and that's basically what I've spent my career studying.
The whole idea of dark energy is like so bonkers, and I want to talk about it in depth, but we can't. Why don't we talk, though, about what it took for you personally to get to the position that you're now in?
Yeah, so I started, like, what year are you guys in? 10978, I heard. Something like that. So I did high school actually in Sydney, and I always liked science and maths, but I didn't really know what I wanted to do. But I did love science fiction stories. I liked all of the like space travel and space exploration stuff. And so when it came to choose what I wanted to do at university, science seemed like a really cool thing to do. So I studied, went and did a science degree. Actually, I also did science and arts, so I simultaneously did an arts degree in philosophy and a science degree majoring in physics. I partly chose physics because it had the most options, it was the most flexible, you could do lots of different things while studying physics, more so than you could biology or chemistry or something like that. So that's what I ended up doing, but also because there was an astrophysics major and you do like space subjects during your physics degree there, and I was like, awesome, that sounds like really, really good fun. So I did my undergrad, which is like 3 years, and then the final 4th year of undergrad, you can do something called honours, which is a year where you do half coursework, so you do half study, but then half research. And so they give you, and this is really funny, because they give you a question that no one knows the answer to, and say you can figure it out. So usually, when you're usually doing your problems and stuff, that you can look up the back of the book and the back of the book has the answer in it. And so in honours, basically that's the first time where you're doing something where there's no back of the book.
You're looking at the back of the book going, there's nothing here.
Yeah.
You've got to write it.
Exactly. So I remember going to my supervisor at the time who was guiding me in this research, and I'd been like sort of bashing my head against a brick wall, not being able to figure this out. And I've gone, okay, I tried really hard, but I haven't been able to figure out this thing. Can you tell me where I can look it up or who I can ask? And he was like, no. I was like, I'm not trying to cheat or anything. Like, I need some help. I can't figure it out. And he's like, no, I don't mean like, no, you're not permitted to. It's like, no, you can't, because nobody knows the answer. That's the whole point of research. You're doing something that nobody knows the answer to. And
what was the question?
Ooh,
what was the question you were studying in your honours?
Can the expansion of the universe go faster than the speed of light?
Can it?
Actually, yes. And they gave me this, basically the problem was, so
how?
We all know now that nothing can go faster than the speed of light. That was one of Einstein's insights, and that measurements and stuff have shown that that's the case, that nothing can go faster than the speed of light. So if you shine a light beam, no particles or anything will ever be able to overtake it. However, space is exempt from that rule. Space itself can stretch faster than light can travel. So you have a galaxy here and a galaxy here, and they're moving away from each other, and basically the space between them is all stretching. And the light is trying to race to go like to one of these distant galaxies, and if the space is stretching fast enough, that light will never actually reach it. And that was the thing. It's the same reason that light can't escape from a black hole, because black hole is like a waterfall of space falling towards the center. Yeah, bit crazy. But they gave me one paper from one author saying, yes, the expansion can be faster than the speed of light, and another one saying, no, it can't. And my supervisor was just, I don't know which one of these is right. Can you please tell me? And that was my project.
So that was your honours year. So that's like you've done a Bachelor of Science in Physics. Mm-hmm. You've done honours year. You've solved a massive problem with the universe. Congratulations. And then you decided to stay and study a little bit more. Yeah,
well, at first I was like, well, I got to the end of honours and we'd basically figured out the answer. Yes, things can go faster than the speed of light. But we hadn't quite finished it and hadn't quite published that yet. So I was like, oh, I'll stay on for a little while and I'll give that a go. So I stayed on, not intending to stay at the same place for a whole PhD, but I got so engrossed in that, and then going into other questions like black holes and can things escape from a black hole, and does the universe have an event horizon just like a black hole does? Turns out that it does. If you go far enough away from Earth, you're never going to get back, even if you don't go into a black hole. I know we won't go too deep down that rabbit hole, but there were so many cool, interesting things that I just ended up spending another 4.5 years actually studying similar questions and answering some really cool fundamental questions about the universe like that.
So that's your PhD.
Yes.
So now you come out, you're Dr. Tamara Davis, and everyone has to call you doctor now because you've done that.
Yes.
So that's when you just go off and stop studying, right? Right?
Well, not really. So at the end, as I was getting towards the end of my PhD, I was at a conference down in Canberra, and one of the professors there was like, oh, so Tamara, because I'd been sort of engaged, I was asking lots of questions. They're like, I hear you're finishing your PhD pretty soon. What are you doing at the end of your PhD? I was like, well, actually, and it's a slightly funny story. One of the things that you sort of expected to do in your after your PhD, if you're doing research, is to go explore the world, go and do some postdoctoral fellowships, which is the thing that you do after your PhD. It's like sort of 2 or 3 year jobs, and you go and explore different places, learn from different people all around the world, like the best scientists around the world, and gather all of that knowledge. And I was like, well, I actually have to stay in Australia for 1 more year because I'm playing there. Has anyone heard of this obscure sport called ultimate frisbee? Yes?
Tamara is literally a world champion.
Almost. I was captaining Australia at World Championships for ultimate frisbee, and I had to stay in Australia for a year to train. And so I was like, I know I'm meant to go overseas, but I sort of need to stay in Australia for a year. And he was like, okay, I reckon I've got something for you. And he sort of made up a job for me and recruited me. And that's when I started work on designing a space telescope to try and measure dark energy more precisely.
So that's a different kind of job than if you're staying within the not confines. You're staying within a a university setting where you're continuing to study. And that's not the only career path you can go with a PhD.
That's right. So at the end of a PhD, there's a huge number of options available to you. And so some of my colleagues have gone into, so I stayed at a university, that I went to the Australian National University after my PhD at University of New South Wales. But some of my colleagues that I studied with went on to do stuff in the energy industry, doing research into clean renewable fuels. Some others went and did banking. Some went into medicine. There was a really cool project where using some of the astronomical techniques that we use to take really clear images of the sky, one of my friends designed a new way to do radiotherapy that made much cheaper radiotherapy things to treat cancer. And so using some of the same focusing techniques, it's a really cool thing where you move, what the usual radiotherapy thing, it needs a big room and a big equipment, and you sort of fire the zappy thing from all different angles so that you didn't target the tumour. But she designed a way where you can spin the person instead of spinning the machine. And usually that's difficult because people's organs move around as you move and stuff, so it's hard to target them if they're moving. But because we do this active targeting in astronomy, she had a way of doing that and translated that into medicine. So there's heaps of different things that you can do once you've got the training from physics, even just at the undergrad level. You basically get taught how to turn real world problems into maths and solve them and find the best optimal solution. And that's just in demand in so many places. So it's a really fundamental skill to have.
So but you didn't do that. You stayed and you did a postdoctoral fellowship, and now you are a professor with a postdoctoral people working for you, including Josh Calcino. So here we have two generations of science. Josh, can you talk about what your professional relationship is with Tamara?
So Tamara is formerly my PhD supervisor. But I actually met Tamara. Tamara mentioned you do an honours year in university. Well, I finished my undergraduate degree, and I finished it in physics and mathematics, and I really wanted to go and do astronomy. So I went across to the University of Queensland and started a project with a guy named Michael Drinkwater. And I thought his project wasn't too exciting. But then there was this really fun, bubbly, don't tell Michael, really fun, bubbly, super energetic person that was like, keen to get me on as a student. So I started working with Tamara on a project, and then did my honours with her, and then all the way to a PhD.
So we heard a bit about Tamara's research work before, but what science have you pioneered?
So when I started my research career in astronomy, I was very much following the footsteps of Tamara. So I was, my very first project was studying things called supernovae, which are exploding stars, and you can use these things to actually map the expansion of the universe because they are what we call standard candles. So they have about the same luminosity, and if you know how bright something is intrinsically, like you have a 100-watt light bulb, and that 100-watt light bulb is 100 meters away, you know how bright it should look to you. So if you don't know how far away it is, you can just measure how bright it is and work out the distance. And so this is a technique that people use a lot now to map the expansion of the universe. So I was studying supernovae, and then I moved on into studying something called primordial black holes, which are like black holes created in the very, very early universe, and they could potentially explain another dark thing in the universe, something called dark matter, which is basically there's 6 times more mass in the universe that we cannot account for visibly, but we can see its interactions gravitationally. So it makes galaxies spin faster than they should otherwise, and it makes these large-scale structures in the universe that the particular structure would not be the same without dark matter there. And then I really went rogue and went to a completely different field in astronomy and started doing planet formation. So I went from big, grandiose cosmology, what's the origin of the entire universe, to the origin of places like the solar system. And that's where I am now.
I remember when he came to me in my office and he's like, Tamara, so I've given him an awesome project, a really good suggestion for research, and he's come along and he's like, hey Tamara, you know that project that you gave me? I think I found a better one. And he just said, I was at a conference and I saw this presentation on this stuff and it's really cool, and I think it's something that I've got this, I think I can help answer this question, and it's something I'd really like to work on. Would you mind if I sort of shift my project and do that? And as a supervisor, although I was like, hold on, come on, my project was a really good one. At the same time, I'm like, that's awesome when you see your students get sort of growing up as researchers so that they can identify really cool problems themselves and go on and say, not only do I figure that this is a really cool problem, I think I know a way that I can go and solve it. Yeah. That's the best thing possible. So I'm like, yes, awesome, go do it. That sounds great.
I think that's also just the beauty of physics and mathematics. Like, if you know physics and mathematics, you can go and solve so many different problems. So
it's crazy to think about the different kind of career paths in something that you might go, like astronomy is a thing or astrophysics is a thing, but you're looking at really, really big, massive scales, and even though we think of the planet that we're sitting on as being quite large because it can fit all of us into it, they're tiny in the broad scheme of things. Like, you've kind of gone from like macro stuff down to like almost microscopic on a universal scale.
Yeah, it's like I've gone from studying this table to like studying almost the atoms in it.
So can you take us through, we heard a bit about Tamara's kind of educational journey. Can you take us through your educational journey? Yeah,
so I mean, I was always interested in astronomy as a child. So I think I was 5 years old, I can remember. Oh God, yeah. A wonderful high school photo. I was always interested in astronomy as a child, so I would love reading books on astronomy and, you know, just fascinated by the planets in the solar system and, you know, just the feeling of the awe of just how big the universe is. There's so much in it that we can learn and understand. And I always had a passion for science. I used to take apart radios and video cassette players, things before your time, but you know what the old thing, what DVDs used to be. And yeah, tinker around with the electronics in them, play around with electric motors and batteries and doing all these weird things. But I was always passionate about science, and I carried that passion through primary school, and then going into high school, I always loved science, but you know, high school is a challenging time. You're all going through that right now. There's lots of changes going on for you right now. But then after high school, I had a gap year. I actually worked at Optus for 1.5 years. Like, yeah, don't want to do this for the rest of my life, and started my bachelor's degree at Griffith University. And I didn't realize you could actually make a career out of studying space. So I was like, I'm going to become a meteorologist. I want to go to the Bureau of Meteorology. I want to go down to Antarctica, do all this cool weather forecasting down there. And then I visited the Bureau of Meteorology. There's 2 people I'm going to annoy tonight. And I actually didn't really think it was all that exciting there. There was lots of people sitting around at desks, but it wasn't really the fun research that I had in mind that it would be. So I had this crisis, like, oh God, what am I going to do now? And then, yeah, that's when I started on this journey of going to the University of Queensland and doing research projects in astronomy. And yeah, that's where it set off for me.
So you kind of know that like high school is 6 years, and then if you do a bachelor's degree, it typically takes 3 or 4 years, and then an honours year. But what about the latter phases of a research career? What kind of timelines are we talking about?
Well, I remember when I was in year 11 and 12, and we were choosing what we were going to apply for at university. People were like, "Oh, you've got pretty good grades. You should try and do medicine or law or something like that." And I was like, "Oh, no, I'm not really that interested in those. I think the science is cool." And also, at the time, medicine and law, they were 6-year degrees. And I'm like, 6 years is the entirety of high school. That's incredibly long. I can't imagine being at university for that long as well. Turns out I spent 10 years at university. Yeah. So I did my undergrad, because I did 2 degrees for undergrad, took 5.5 years to do that, and then 4.5 years to do my PhD. And so that was 10 years at university before I even started my university job. And now I graduated from my PhD in 2004, and I've been at university still ever since then. But typically I went and did this postdoc. So postdoc means postdoctoral. It's after you've got your doctorate. I went and did that at ANU for 2 years, and then I went and worked at the University of Copenhagen over in Denmark. Worked there for 2 years as well, before coming here to University of Queensland, which is where I stayed. And then got a permanent job here and became faculty, and you do a bit more teaching and lecturing at university then, as well as research, and do lots of grant applications and get money to pay other postdocs and PhD students and stuff who will work with you.
And I saw this person who was talking about how much he loved mathematics counting on his fingers just now.
It's funny when you're like thinking of time and numbers in your life. It's like you have to think so hard about how long ago was that.
How long did it take you to get to the position that you're in
So
now?
I finished high school in 2010, and then I had a gap year and started university in 2012. And then I graduated my undergraduate in 2014. And in total I spent, on my fingers, nine years at university. I mean, it sounds like a really long, daunting time, especially when, like, if you're 15, it's like 9 years, that's like well over half my life. But being at university is so much fun. Like, you meet lots of cool people, you get to have a lot of fun. And if you love learning, it's one of the best places you can be. So,
Yeah.
I mean, that time has flown by and I've enjoyed it thoroughly.
Yeah,
So.
I thought the university is great. If you do go to university, I thoroughly encourage you to go and join all of the clubs and societies and things that you can at university, all of the sports clubs. That no matter what you're interested, there's going to be a club at university with a whole bunch of people who are also interested in that, and get involved in all the social parts of university. You actually learn a lot there. So like by helping run the Ultimate Frisbee Club at university, I learned how to like write budgets and organise people and organise teams of people, which ended up being really, really useful when it came to doing research projects. So the kinds of things that you learn in the classroom are only part of what you learn, both at school and at university. The sort of extra things that you do outside of the classroom are also really important stuff that you're learning.
So you guys are really busy pioneering science, but what does that actually look like on a day-to-day scale? Do you sit around like stroking your chin a lot?
Yeah.
Do you just have a telescope in your office?
Just sit there going, can things go faster than light? I don't know.
No.
For me, and well, for astrophysics research especially, there's some of it is like figuring out what you have to figure out. So you might be reading books or reading what people have done in the past and doing some calculations and figuring out, well, maybe we need to improve the equations in this way, and if we do that, that might match the observations. And then some of it's going to telescopes and observing, but a lot of it is actually computer programming. So for my research, and for yours too, right?
Yeah, it's a lot of computer programming. So I hear that kids these days actually learn coding in school, which is great. Never had that experience. I had to learn that pretty late in my university career, but you spend a lot of time writing code, but it turns out that's a very employable and highly sought after skill at the moment, because most of the workforce doesn't know how to do it, and it's a very, very powerful tool. Like, I mean, if you know how to code, you can you can design a robot, like you can tell a motor how to move in a particular way, or you can run simulations of how planets should form, or you can compute how the universe should have expanded over time. Coding is an incredibly valuable tool, and it can be pretty fun as well. You can do fun projects with coding.
Yeah. So Josh did some amazing simulations that have pictures of how the gas around a star would form and planets might form in that star using the coding. And when I was doing my undergraduate, I also had a project where I was working in a firm that did steel manufacture, and I used some really basic coding to help them streamline their processes of buying and bending steel and welding steel and all of that sort of stuff that saved them a lot of money. So it's the same kind of stuff that, you can figure out how planets form, you can use to work in industry as well.
Yeah.
So if you're doing research that's answering questions that no one else knows the answer to, and there's no answers in the back of the book, how do you actually know that you've got it right?
That's a great question. Sometimes you don't initially.
Yep.
You're I don't know, you can answer, I've been talking
I
a lot.
mean, so when you're doing research, it's not just doing research, you have to be able to communicate it, right? You got to be able to tell other people what you've done, how it's relevant, why, and what you've learnt. So we do that in a research paper, and we submit these research papers to journals. And basically, these things get published, But before they get published, they go through a process called peer review. And then other people, generally, they're anonymous during the review process. They will read your work and critique it. And
These are other experts in the same field.
Yes, a person in the same field is what you're working in, and then they'll critique your idea and try and find flaws in it, and then send you a report back about how you did. And if you pass that, then your work will go into the literature, and it might be years down the track, someone might come along and go, actually, this work was wrong. And that happens a lot in science. But usually it's not like it was completely wrong. It was like mostly right, but there was this extra thing we could do, and now we can explain this other thing.
Yeah, so it's a constant process of improvement.
It is.
So you come up with, so there's, a really big example is we have Newton's theory of gravity. Now, it was supplanted by Einstein's theory of gravity, general relativity. Now, Newton's theory we still use to build buildings, to build bridges. We use it to calculate how a ball flies through the air and how it's going to land. You don't actually need Einstein's theory for that, because if something's moving slowly and it's in a weak gravitational field, which the surface of the Earth is a pretty weak gravitational field, Newton's theory does just fine. But it fails if something's moving fast or if it's in a strong gravitational field, and that's where you need Einstein's theory. So Einstein came along and was like, that Newton stuff's okay, but here's an improvement, and this, if you do this, it will explain things like the orbit of Mercury. And these days, the thing that Einstein's theory is most commonly used for is if you have phones or anything like that on you, in GPS. Because the GPS satellites that it's pointing out, that blue dot where you are on the map, they're in a different gravitational field. They're outside they're orbiting the Earth, so they're in a weaker gravitational field than Earth, and they're moving fast. So if we only had Newton's theory of gravity, we wouldn't be able to do the calculations of where that dot is on the map. It's Einstein's theory that explains that. So that's sort of and right now what we're doing is, one of the things that we're doing by trying to explain dark energy is trying to improve on Einstein's theory. So we've gotten this far with our theories, but we know it's not the end. We know there's more to the story, and we're trying to find the next theory that improves on Einstein's theory and can explain even more than that one can.
So can we talk about, if you'd taken the advice that parents were trying to give you when you were finishing high school to be a doctor or be a lawyer, you know that the job of a doctor is to save people's lives, that a lawyer is to win court cases, but what is the ultimate goal of a research physicist?
Figure out how the universe works.
Yeah, figure out how it all works. And when you understand how the world works, you can make it a better place. Like, if people 500 years ago, before Newton, didn't really care about how the world worked, we wouldn't have these lights, we wouldn't have these TV screens.
But you never have an answer. You have an answer that just becomes another question, right?
Yeah. So my particular field of research, so I study planet formation now, that's my main gig. We can observe these things called protoplanetary disks. So when a star forms, it's basically you've got all things called molecular clouds. If you go out in a dark night and see the Milky Way, you'll see dark spots in the Milky Way. These are molecular clouds, and inside of these molecular clouds, there's dense regions which are collapsing under gravity and forming stars. And not everything will fall onto the star. If I was spin around on this chair and bring myself in, I'd spin a lot quicker as I bring myself in closer, just like an ice skater would. So not all of the material lands onto the star, so you get a disk that forms around it. And in this disk, planets have to form. All the comets and asteroids and everything that we see in the solar system, they're leftovers of this disk. So the ultimate question for my field is, how do we go from these disks that we see to a fully formed system like our solar system?
Mm-hmm. Yeah. So we're trying to, solve the question of where did we come from as humans? Yeah. How did we get here? How did the universe form? Will other universes form? Do other universes exist? And then how do the laws of physics work, and what can we do with them? If we can figure out ways to harness things like dark energy and dark matter, who knows, maybe we can harness these. Maybe we have a new clean source of energy. We want to try and figure out things that can improve ourselves as humans, but also we're just curious. It's just really fascinating to try and figure out what's going on.
So we've talked a lot about your relationship with Josh and how you've mentored him. Who was your mentor as a postdoc?
So after I finished my PhD, I mentioned there was this professor at that conference in Canberra who invited me to do a job down in Canberra. His name was Brian Schmidt. And he was one of the ones who had just discovered that the expansion of the universe was accelerating, which was a really, really big deal. And he's been a fantastic mentor to me for my entire career since then.
That's right. So the young man that we were talking about from Alaska at the beginning is Brian Schmidt, and he's actually going to join us live now from the Australian National University. Tamara's postdoc supervisor, Professor Brian Schmidt, welcome.
Hi, Brian.
G'day, good to see you all.
Hello, Brian.
So, Brian, some in the audience might know who you are, but for those who don't, can you tell us about yourself and the science that you've pioneered?
Sure. So obviously I'm Brian. I grew up in the rural parts of the United States, Montana and Alaska, sort of up in the mountains. I never thought I would be an astronomer, but decided to be when I didn't know what else to do with my life. What use is an astronomer, I thought? Well, it's very interesting. Never thought I would be able to be an astronomer. Ended up doing a PhD and then immigrating to Australia in 1994. So the reason I came to Australia is one of the best places in the world to do astronomy. And I was given the opportunity to do an experiment where we could look back in time and see how the universe changed and how fast it was expanding. And why would I want to do that? Well, I wanted to go through and see if the universe was slowing down and really how much it was slowing down. We knew it would be slowing down a little bit or a lot. And that allowed us to, if we could measure it, to see the trajectory of the universe into the future and try to figure out, is the universe going to exist forever? Or is the universe eventually going to stop expanding, go in reverse, and create what I like to call the Gnab-Gib, the Big Bang backwards? Realized that I've stolen that from Douglas Adams without realizing it for about 20 years. The amazing thing, of course, was in 1998 when we measured, the universe wasn't slowing down a little bit. It wasn't slowing down a lot. It was actually speeding up, which is exactly what it was not supposed to be doing. And so that is the big discovery that we were part of, that the universe is speeding up and it must be therefore full of something we didn't expect, stuff we call dark energy now, which we think is about 70% of the universe.
And has anyone ever given you any reward for your research? Any big ones?
I have been rewarded very often in my life. If we look behind me.
Ooh.
Which one is it?
This is probably the big one that I've got. So that's a Nobel Prize.
That's the Nobel Prize.
Sorry to say this isn't the real one.
Oh.
Oops. Oh, geez, I just dropped it.
Don't break it. That'd be a shame.
Well, I hopefully wouldn't have dented. The real one is in Questacon. So it's made out of gold. This is a replica. They give you 3 replicas. You're not allowed any extras. Anyway, so yes, I have been well rewarded in my life, probably over rewarded.
I mean, it's amazing. We've got a room full of awesome young people here looking at you. You're sitting in your fancy office with your Nobel Prize. But what did it take for you to get to where you are? What was your research trajectory?
Well, pretty unremarkable, really. I started out growing up in the sticks. I mean, we're talking the moral equivalent to back of Burke. Anchorage was the biggest city I grew up in as a child up in Alaska. So that's sort of like growing up in Darwin, I suppose, would be the equivalent here in Australia. And then the other places I grew up were much smaller communities and in intensely regional parts. So I never really had much expectation of being anything other than just a normal person going out and doing their job. But in the end, what I have found is you keep positive, you do your best, and sometimes you're part of something big that you didn't intend to be part of, and you get the opportunity to make a contribution beyond any expectation. And it doesn't always happen. And indeed, making such a discovery as the accelerating universe probably hasn't made me particularly a happier person, but it sure has made life interesting. And someone has to do it. And, when you look out at your audience, those are the future people who are going to be making discoveries. And we have to remind ourselves that people make discoveries. And I've had a chance to meet who we would say are the smartest people in the world, all of them. Not me, I'm afraid. And they're all just like me in the end, quite normal people. Normal people do amazing things, especially when they work together.
So we've been talking about sort of generations of science, and we heard a fair bit about Tamara mentoring Josh, but you were Tamara's mentor. What's it like being a mentor?
Well, it's not hard. Being a mentor is great. You get to sit down, you get to talk to someone, learn what their passions are, what they want to do, and you help them. And you can go through and say, well, what is it you want to do? And Tam's the first time Tam and I started hanging out was when she was trying to finish her thesis, and I suggested, well, she was pointing out very important astronomers' mistakes. Probably to do it really nicely would be a really good idea.
That's
So that
right.
was
I
my
remember
first
you were
piece of
telling me
mentoring
that
I ever gave Tam.
that was the first piece of advice I remember, because I was publishing a paper that, you know how I said at the beginning there was like some papers said one thing and some papers said another thing, and I was pointing out all of those papers that were wrong, and a whole bunch of famous people had said the wrong thing, and Brian was like, you might want to be really nice when you tell them that they're wrong. It's like,
Yeah, and can I say that was good advice?
yes.
I feel like the role of a mentor is a relatively obvious one. It's to sort of bring someone up and guide them. But can we talk about the role of the junior scientists in this scientific ecosystem?
Mm-hmm.
Tamara?
Yeah, the junior scientists really are the ones who get a lot of stuff done. Once you get into the senior roles, you're spending a lot of time writing grants and doing lecturing and stuff, and your time gets more and more scooped up into sort of managing science and making sure that the whole thing happens. Taken to the extreme in Brian's case, who's now Vice Chancellor of a university down at ANU. Whereas when you're doing your PhD and your postdoc, those are some of the funnest times, or at least I found it, so, of your scientific career, because you don't really have any other responsibilities yet. You can really just chase the interesting ideas and go deep dive and research into whatever you find is like the most interesting question in the universe. And so they're some of the really productive times of your research career.
And I guarantee you that when you look at news articles and you see something really cool in news that scientists have found this and so on, so a lot of the time they're grad students, PhD students leading those research projects, and they make it onto the news. They make it onto the ABC, and you can do lots of really cool stuff while you're young like me and have time, young like you.
Brian, your thoughts?
Absolutely. Young researchers are at their most creative. They've just been armed with all the new technological advances, and their lives have not been fragmented because, doing leading edge science, part of it just requires focus, and that's what you're working on. As you get into TAMS and my time in life, you get to work a bit, but your life gets fragmented. And so wisdom is important. It's always good to have that wisdom and sort of a bunch of experience about what are blind alleys. And so I always think that young scientists working with older scientists creates a team that is really effective at doing research.
Mm-hmm.
Who was your mentor?
Well, I had a number of mentors. My PhD supervisor was a scientist named Bob Kirshner. We still do a lot of things together. He was a Harvard professor. But I also had the likes of Nick Sunseth, who was an astronomer down at Cerro Tololo Observatory in Chile. And indeed, he and I are the ones that formed the experiment that led to the Nobel Prize. Uh, but the reality is, I was a bit of a mentor hoarder. I ask everyone for advice, and I still do. I call up people all the time. Help me. What do you think? You know, it's really good to get a bunch of diverse perspectives, and I often ask people who are very different than me for advice because it's good to think outside the box. Really important to solve hard problems.
It's not a solitary endeavour, science, is it, Tamara?
It's definitely not a solitary endeavour. We work in, especially in astronomy now, we work in really big teams. But even if you have done something and figured something out on your own, it doesn't advance science if you keep it to yourself. You have to go out and talk about it to other people. And it's interesting how much communication is important in science, because you have to be able to convince people that your ideas are right. And that's part of the thing where you go through the trials of getting your idea out into the mainstream. You have to really convince people, and you have to be able to argue your ideas and explain why your stuff is right. But it's by no means solitary. Like, we have these sort of generations of scientists where we're working with mentors who have sort of established this field that you're trying to learn from, and then you come up with your own new advances, and then you become the mentor. But at the same time, we work in big teams. So especially for astronomy now, we're working in teams of sometimes hundreds of people spread all around the world. So I'm working on something called the Dark Energy Survey at the moment, and that's got about 500 researchers on at least 5 continents. And we are all working together trying to get the best possible data so that we can figure out some of the mysteries of the universe.
It sort of feels like science is like building a never-ending staircase, that each generation's sort of building the next step. And so we've heard about the step that Brian built and the steps that you're building, and then yours as well, Josh. What comes next? Like, somewhere out in that crowd there could be your postdoc. What are they going to be studying?
Well, I think for me the most exciting thing that's on the horizon in research in astronomy is finally being able to answer the question of whether or not there is life on other planets orbiting other stars. So by the time that you're maybe at my stage in my career or a bit after, we will have telescopes powerful enough to answer that question. They'll be able to look at the atmospheres of Earth-like planets orbiting other stars and look for the key signatures of life, to look for oxygen in the atmosphere, to look for the waste products of life like methane, or maybe even industrial pollution. So these things we will be able to detect. We could even, there's ideas of looking for you ever been on a boat or over a body of water and the glare bouncing off the water hits your eyes? It's really quite annoying, but that's actually super useful if you want to work out if there's oceans on another planet. You can look for that glint. And you can look for, say, as a planet is rotating, slight changes in the color of the planet. Does a color match what we would expect a planet to look like if it had plants or if it had an ocean? And so these things are things that we're going to be able to answer in about 15 or 20 years. So that's what I'm really looking for. That's like from me growing up, is there life on other planets? And to be able to say that we will be able to answer this soon, or at least start being able to try and answer that question, I think is very exciting.
So that's the planet sphere, for want of a better word. What about in your realm, Tam?
So we're, in the cosmology realm, we're really trying to figure out the laws of gravity and quantum physics, the laws of physics, and figuring out how they work together. So I said before, we've got like Einstein's theory of gravity, general relativity, and in that theory, time can warp and bend, and space can warp and bend, and that's what makes things orbit and move. And we have quantum physics, and in quantum physics, it explains all sorts of cool and weird stuff about particles. And they're both super successful theories, but we know that they both can't be perfectly right because they don't perfectly work together. There's no warping of time and space in our equations for quantum physics at the moment, but we know that that has to be there somehow. And so we're trying to figure out how those two theories work together. And the reason we're excited about this from a cosmology point of view is Brian's discovery of dark energy might need those two theories to be merged to be able to explain it. It might be a quantum physics effect, like the energy of the vacuum itself, that explains this dark energy. And so really we're on this, it feels like we're on the precipice of being able to figure out a new theory that does better than any of the theories of physics before us, and that's the sort of cool thing that we're aiming for.
Brian, what are you excited to see the next generation of scientists pioneer?
Well, I hope I get to do a little bit of it as well, but I have the luxury of being able to work on many things. So I have worked a bit on planets. I, of course, work a bit on the cosmology. And then the third thing that I think I'm very excited about is that we're building a whole range of new generation telescopes. So this is the James Webb Space Telescope. This is the Square Kilometer Array Telescope. It's ALMA over in Europe, in Chile, which is sort of a consortium of most of the world. And what they're allowing us to do is to look back so far in time to when the universe started getting interesting, and essentially seeing the baby pictures of the universe and how stars and galaxies formed. So over the next decade or so, we're literally going to have the place where we've got the family photo album, and suddenly revealed are the baby pictures of the universe, so we can see what we looked like when we were infants, because we get to see what we look like right now. They're all recent photos. We have that beginning of the universe where we really get to understand it. And I think that's going to be really exciting.
So we've got like the ultrasound picture, we've got the now, but we don't have the baby photos yet.
That's absolutely right. Couldn't have said it better myself.
So we heard before that our audience is people in probably the first half to 2/3 of high school. Josh, what do you wish you'd understood about science and just like what to do after school when you were at that stage?
What would I have liked to have known? I can't pin down on one thing. It's all experience. I mean, you spend a lot of time in high school worrying about things that really aren't that important, I think. If there's one skill I could have learnt, it would have probably been coding, because that is an incredibly important skill. But you're all learning that now, so for you, it's obviously going to be something else. But I think, not even about skills, but I think the most important thing that you can try and get for yourself now is a passion for something. So it really doesn't matter what you want to do, whether it wants to be science, finance, medicine, anything really. Just try and find the passion to do it, because it's really hard to motivate yourself to do something that's difficult unless you're passionate about it. And anything that's worth doing is going to be difficult. So you've got to be ready for these challenges, and being passionate and motivated will get you through them. And that might end up getting you a Nobel Prize like Brian over here.
Yeah, well said.
What about you, Tamara?
I actually thought of something, I hadn't thought about this for ages, but I remember when I was in year 12 and moving out into university, I remember being terrified of the fact that there was not going to be age groups anymore. So, you know, when you go to like a sports carnival or something, you're competing against people in your age group, and then you're doing exams and stuff with people from year 12. And it felt to me like when I was going into university, now I had to be competing against the entire adult world. And I was terrified. I was actually really intimidated by that I didn't know how I was going to be able to compete on that scale, and like what my contribution could be. And it only dawned on me after quite a few years that you are always still in age groups. Like you're not, when you start university, you're not going to be judged against the entirety of everybody who is like the top researcher in the world or something like that. You're still working, people expect of you what you can expect of someone in that age group. And I don't know if this is profound or silly, but if I had realised that sooner, I wouldn't have been as daunted by some of the challenges that came up when I started doing university and things. So maybe that's something.
Brian, anything that you wish your teenage self had had?
Yeah, I think what Josh said really resonates, and I guess just building on that is it's really important to have confidence in yourself that you're going to go out and you're going to do the best you can. Now, I can't guarantee best you can is always going to be enough, but normally it is, and it's all you can do. And so rather than worrying about the competition, worry about doing the best you can. because that's all you actually can do. And 99% of the time, it's all that matters. And the 1% of the time, it doesn't make any difference because you won't have enough information to even know that you're in over your head. You have to try and be prepared to fail. And if you fail, and let me tell you, I've failed a few times in my life, trying the best I can, and then you're like, okay, always wanted to be a great French hornist, and I tried hard, and I even toured Australia playing the French horn, but I was not good enough to become a great French hornist. I was always going to be a mediocre player of the French horn. Indeed, I played in Brisbane in 1985 from the Anchorage Youth Symphony. So that confidence to do your best and know that the world looks after people who try hard and are good people, and it doesn't look after nasty, highly competitive people who try to knife everyone else in the back. Then you're on your own, and good luck, but don't expect any help from me.
Yeah, I've got something else similar to add, is that don't worry too much about the distant future. You never know what opportunities are going to arise.
That is literally what you do, Tamara. You're always worrying about the very, very distant future. It's your job.
Okay, I'm worried about the future of the entire universe, but I'm not worried about what I'm going to be doing in 2 years' time necessarily, because you never know what opportunities are going to arise. And a lot of the projects that I have taken on or done in my career are things like that. I was having a beer at a barbecue at a conference in Canberra, and Brian says, "Hey, Tamara, do you want to work on this project with me?" And I'm like, "That sounds great. Let's go that way."
I had a beer at Canberra Airport, and that's how I ended up in Planet Formation.
Yeah. Cool. Maybe we shouldn't be telling this story, too many beer stories. But the idea is that, like, if you're really engaged and passionate and really enjoying what you're doing right now, just make sure that you're doing something that you love, and then opportunities to do things that you love are likely to come up, because that's what you'll be good at. And don't be afraid, even if you thought you were going this way, don't be afraid to go whoop and go over here if you see something else that you think is more exciting. Follow your nose and trust your instincts.
Yeah, I don't think I could have believed that I would be an astrophysicist at your age. I so thought that I was going to become a meteorologist. And Brian, I heard that you also wanted to be a meteorologist. Is that right?
Absolutely. From the age of about 6 onwards, I was going to be a meteorologist. Then I worked at the National Weather Service, and I wasn't so sure, and that's why I decided I don't know what I want to do. Became an astronomer instead, but I'm still a weather freak.
I love it too.
You need to be a weather freak if you are worried about both whether your telescopes can observe and whether your grapes will be able to be harvested.
Yeah, let's not talk about grapes and harvest right now.
So we have a couple of minutes for questions. So if you've got questions about either the origins or ends of the entire universe or just careers in science, chuck your hand up and ask our brainy brains up here. Yep.
Can I ask your opinions on the Big Bang?
Our opinions on the Big Bang.
What, the TV show, or?
Well, we've observed it. The Big Bang is the theory. The Big Bang theory is the theory that we have for how the universe began and things, and there's an enormous amount of evidence for it. And so we can actually understand, if we model from a fraction of a second after the very, very beginning and model forwards, we can predict patterns that would happen in that really dense early part of the universe, and we can predict and model how galaxies would form. And one of the projects that I did that was mapping hundreds of thousands and now hundreds of millions of galaxies is using that distribution to confirm the predictions from the Big Bang. And so that it's been confirmed in so many ways now that it's just really, I don't know, solid.
Excellent. Another question? Hi.
So you said you had a telescope that could look back in time.
Your telescope looks back in time. Explain.
Who did you use that to see if there was life on other planets?
Yes.
So the question was, the telescope, you say you got a telescope that could look back in time. Can't you use that to tell if there's life on other planets?
Well, I mean, light takes time to travel, right? So if we're looking at a galaxy 2 million light years away, we're seeing the light from that galaxy 2 million years ago. If there was a mirror 33 million light years away from Earth that we could look at ourselves in, we would see dinosaurs on the Earth. But I mean, that's to look for life on another planet. It's all about resolution. You know, like we've got really good phone cameras on our phones these days, but to be able to like resolve life or resolve features on another planet, you need a really incredibly large telescope, like something like space-based, but like taking up a good fraction of the whole solar system.
Wow.
But I mean, in principle, if humanity flourishes for the next few hundred years, maybe something like that would be possible. You just never know.
Another question? Yeah.
When you're in university for like 8 years, how do you keep yourself stable and get money?
Where do you get your money from if you're at uni for 8 years?
You're
Great
into the
question.
real struggles of life here now.
So for me personally, I worked in a couple of factories I think in the offices of factories, so helping the factories run. I mentioned before that I was working in a steel manufacturing plant, and that was actually really fun because we were building like massive buildings and stadiums and stuff, and it was really cool to use all of the maths and stuff I was using in physics to figure out how to construct something like the theatre that we're in right now. And so I worked up, depending on the year, but up to like 20 hours a week in work, as well as doing, I had 24 hours a week of classes, and then this was for science in undergrad, and then all the homework and stuff that went with that. But then when I got into higher years, I did some tutoring, and they had, like, once I was in fourth year university, they have you helping tutor the people who are in first year, and you get paid for that as well. And so basically did a whole bunch of work until you get to a PhD, when you get a scholarship to live off, and then you can also continue to do tutoring and stuff like that to get bonus money as well.
I think we've got time for one more question. Yep.
You mentioned earlier that the universe is expanding faster than the speed of light. Could you explain that in a bit more detail?
Okay.
Explain in more detail how the universe is expanding faster than the speed of light.
So the universe is, basically, the velocity of a galaxy moving away is proportional to its distance. And this is, so a nearby galaxy is moving away from us relatively slowly. The one bit further away is moving away a bit faster. And so at a particular time, everything is moving away from everything else. And if you go far enough away, you just get to galaxies that are moving faster than the speed of light. And the weird thing was, usually if it was something that was moving through space, when it got close to the speed of light, you would need to do special corrections, relativistic corrections, to take into account the general relativity theory of gravity, or the special relativity. But it turns out that the expansion of space doesn't need those corrections. So the expansion itself can be faster than the speed of light.
Do you want to talk about raisins in a cake?
The raisins in the cake?
Is that a good analogy?
Yeah. So it's like, if you think of the galaxies sitting in as raisins in like raisin bread or something, and you have the dough and you put it in the oven, and when you bake raisin bread or something, that expands, and each raisin will move away from every other raisin. And so there's a cool thing about this, is that when everything's moving away from everything else, there's no center that it's moving away from. But every galaxy is moving away from every other galaxy. So you could pick any point in the universe and everything else would be moving away from it. And so the sum of that story is that I'm telling you right now that you are the center of the universe, because everybody's the center of the universe.
That's my main takeaway from today. Look, thank you all so much for coming and listening so respectfully. Thank you, Brian, Josh, and Tamara, for your expertise. Go and add some science subjects to your plans for senior. See ya.
Thanks, everybody.
Thank you.